Short format. You can read a paper format. Definitely you can. You can ask ChatGPT to pay for it.
And it'll do a terrible job.
It will do a terrible job, but you will have read the paper.
Okay, yes. Well, not you.
That's
Okay, that's a good answer. Some reviewers do that.
I would imagine they do.
Yeah. Right.
Looking at some of the lectures, the slides of the lecture, I would assume that that's
Yeah, exactly.
Well,
you stop all that.
one get them down for yes. Did you select
Invest in more interesting areas.
These aren't
Yes.
very good. We
Fundamentals.
what we have. And not
All right, let's see what will happen.
So, yeah.
Did you start the live stream already? Okay, good. You are quick.
And I still think like this binary
Hello.
like this plot, I think you should just put it like this.
Here is better? Or should I do it here? You don't know? Is it better? Is it okay? Well, you don't know if it's better because I didn't try that one much. Okay.
I mean, like, yeah, this explanation.
Good.
This is kind of.
Everybody's so quiet. And the bell didn't even ring yet. Do we hear it from here? Yeah. We can prefetch and start early. Everything's good online? Okay. Okay, now we can get started officially. Okay, this is lecture 11. I think we have only 3 lectures left. Am I correct? Or something like that. If you do approximate computing, approximately 3 lectures left. Now you know why you don't do approximate computing that much. Because in some cases, you want to know exact numbers. In many cases, in fact. Okay, today we're going to talk about memory-centric computing. This is going to be probably the most research-oriented lecture of this class, maybe with the exception of one more. Let's see. Although I say this was true, especially when I was giving these lectures in 2013 or so. But today we have memory-centric computers in the sense that you can buy them, you can program them, you can put applications on them, you can even abuse DRAM to actually get some computation done. So we're not that researchy in the sense that things are moving forward toward this. And I think maybe 10 years later, if we teach this course, this may be the dominant paradigm. Let's see. That's our goal, essentially, in research. And it's because of the memory problem that we have discussed in this course and that we have looked at processor-centric solutions to it. If you remember prefetching, for example, we spent a full lecture on that, and you did an assignment on that. Maybe we'll do a memory-centric computing assignment in this course in the future iterations, but not this one. But if you take computer architecture, you'll see a lot more material like this. Let's see if I can cover everything in one lecture. So this is another way of thinking about enabling fundamentally efficient computers. Basically, the problem we're targeting is computing today is bottlenecked by data. And important workloads are data intensive, and they require rapid and efficient processing of large amounts of data. And this problem is getting worse because data is increasing. You can hear me well, right?
Yes.
Okay.
I'm just thinking that maybe you're hiding part of the screen.
Oh, I'm okay, covering the screen. Okay. I should not cover the screen. You need to find a strategic placement of data, which is a problem in memory-centric as well as processor-centric computers. Okay, basically, we generate a lot more data than we can process, and we need to perform more sophisticated analysis on more data. People are basically very demanding in terms of what they want to do. And you've probably seen a picture like this many times. I'm not going to harp on it. Essentially, requirements of neural networks, large machine learning models, foundation models, LLMs, whatever people call them today, is growing in terms of both memory requirements as well as computation requirements. As a result, people are experimenting with new architectures, like these folks from Cerebras are looking at wafer scale chips so that they can put huge amounts of memory together with huge amounts of computation. Except the huge amount of memory they have is 40 or 80 gigabytes. It's not that big, basically. It's very small if you think about it, whereas the data requirements are growing a lot. And there are data generators that are very good. Clearly, machine learning, there's a lot of data generated, but in genomics, a lot of data is generated as well. We're going to talk a little bit about genomics, very little in this lecture. There's going to be an overview lecture as opposed to a lot of detailed lecture, but I'll go into some detail on some techniques. But basically, you can have sequencers that look like this, and that can generate a lot of data. And people have been using these sequencers to actually sequence a lot of genomes. For example, during COVID, a lot of these were used to sequence many, many variants of the COVID genome, etc. Okay, basically, I could keep going. Video is another example. There are video cameras everywhere, and that generate a lot of data. Essentially, data access is a major performance energy bottleneck. But the way we design our computers, so far we've looked at in the last 10 lectures, essentially waste a lot of energy because processor is here, memory is here, and you need to move the data between the processor and the memory. This wastes a lot of energy because of the energy of data movement. This also wastes a lot of performance, as we have seen, and we tried to overcome with multiple different techniques like prefetching, right? This is interesting because I put this in parentheses. Normally, we don't recognize the energy waste. Most people don't care in general. And that's clear in the machine learning models that we do today, right? But I think people are increasingly interested in the energy because they realize it's also performance. Because if you reduce energy, you can add more processing units. But people have recognized the performance loss for decades and decades. And what did they do? They basically took a processor-centric approach to fix the problem, meaning they added huge out-of-order execution engines. We talk about that, right? A lot of big caches, many, many levels of cache hierarchies, right? A lot of prefetchers at all different levels, many levels of multi-thread, right? We've seen all of these concepts actually so far. And that complicated the system a lot. Now, when these things work, they actually provide performance improvements, and you've seen that in previous lectures. But when they don't work, because the locality doesn't exist as much, for example, you cannot prefetch very well. Out-of-order execution has a lot of dependencies. You cannot cover those latencies, etc. Then they're actually wasting a lot of energy still, and also adding complexity to your system. So most of the system is dedicated to memory and storage. So our systems are very complex. Most of it is there. Most of that hardware is there to actually tolerate the memory latency in the end. And this becomes a vicious cycle. You actually add a lot more hardware to reduce the performance loss, but that actually increases your energy waste. So I think we're in this vicious cycle today. We're wasting a lot of energy. And people talk about sustainability, right? One of the issues in sustainability, one of the metrics is to reduce the carbon usage. And if you actually have a huge processor, most of it is dedicated to actually reducing the data movement problem. Your carbon is really wasted on tolerating the memory latency. Okay, so hopefully I made a case. Essentially, today, computing systems are very processor-centric. Whatever your processor, computing unit may be, CPU, GPU, FPGA, pick your favorite, ASIC, you have to access memory to get the data over there. And at great system cost, you actually do the processing in one place. And this is my picture. It's a picture that I drew in 2008, XFIG, when I first wrote my NSF proposal. We were working on quality of service of our memory controllers, et cetera, memory systems. But the picture kind of remains today, at least in a processor-centric system. If you look at this picture, cores, or if you think about it today, more heterogeneous cores, accelerators, et cetera, are the parts that do computation. This is a single chip. If you can think of it as SoC also. But everything else is there to move and store data. Right? Caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage. And if you do the calculation, more than 90%, 95% actually, of the hardware real estate of a single node is dedicated to these things that don't compute. It's amazing. So I like taking the perspective of a blank slate. You have this picture, and you have a 10-year-old kid. Ask the 10-year-old kid, and they will respond honestly. A lot of people who are invested in it may not respond honestly, but the 10-year-old kid, without any investment, would respond honestly. Give them this picture, say, I'm dedicating almost all my resources and energy to storing and moving data. This should not be a problem, right? They will tell you, are you kidding? This should not be a problem, of course, right? But this is our problem today. So maybe the 10-year-old kid would be honest and say, scrap this, do something better. Okay, so we're going to be like 10-year-old kids in this lecture. And I think we need to be like that going forward. Otherwise, this problem will get compounded and compounded and compounded, and people will keep complaining about how badly we're wasting energy, etc., carbon, marbon, and this will continue forever, basically. So you have to take a different approach. Okay, let me give you that was kind of the hardware resource perspective, right? Let me give you some data now. This is a data. I can keep giving a lot of data, but for the sake of a short lecture, we're going to focus on some data points. This is the paper I like. It's 2015. Google published this beautiful paper where they analyzed the microarchitectural characteristics of their workloads, according to them, all of their data center workloads. And they basically said that most of the time, on a cutting edge processor, these workloads are waiting for data to come back from the memory. These workloads are doing, or the processor is doing what it's supposed to do, meaning finish instructions, only 10 to 20% of the time. Now, again, let's take the hat of a 10-year-old kid. Say, I designed this processor. My goal is to finish instructions as much as possible. This processor is doing what it's supposed to be doing only 10 to 20% of the time. Am I doing a good job? The kid will be honest with you and say, scrap this, right? That's the idea, basically. Okay, so that's performance. Energy is much worse. If you think about energy, this is, again, some data. There's a lot of data over here. I'm going to give you more data on energy, actually, soon. But this is data from NVIDIA 10 years ago. You can argue with all of these numbers, but the trends remain the same. Essentially, a complicated double precision floating point arithmetic operation is 20 picojoules. And a DRAM read or write is 16 nanojoules. This number went down. It's about 1 to 2 nanojoules. You can actually bring it down a little bit more. But still, there's a huge discrepancy, as you can see, right? According to these numbers, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. And this is actually a success of technology scale. Because we were able to scale the transistor sizes and energy very well, computation became not a problem in terms of energy, right? But interconnects and the memory technology did not scale as well. As a result, you get these high energies that you have. Okay, so that was complicated. Let's talk about simpler arithmetic operations, because people want simpler today, and for a good reason, because they want to reduce energy. If you go to simple, let's say 32 bits integer addition, then the discrepancy, assuming the same numbers, is 6400x. So you basically consume 6400x more energy accessing memory. Now, asking the question is important. Do I want to move 2 elements of data to do a binary operation, to do an operation on 2 values into the processor, and then do the simple operation in terms of energy and write back the data once more? I'm consuming 3 times 6400x if I do that. And you can do the calculation. It's an optimization problem in the end, right? How many times should I reuse this data so that I can overcome this energy differential? Now, your reuse numbers need to be crazy, on the order of thousands. And in some cases, you can get that. When you get that, maybe you can make up for the energy differential. When you don't get that, which is many, many workloads and large data sets, then you cannot make up for the energy differential. And again, we're talking about simple arithmetic operations. If you make this even simpler, the differential actually increases. If you make the arithmetic operation, let's say 2 bits, 4 bits, 1 bit, if you're possible. People are talking about 1-bit LLMs, if you can do that, because they're wasting a lot of energy, right? This reduces the data movement cost, no question about that. But this also reduces the computation cost. And it reduces computation cost much more than it reduces data movement cost. Let's say divide it by 32. Computation cost divides by 32, but data movement cost doesn't divide by 32. Hopefully that makes sense, unless you pack your data extremely intelligently and be very careful, etc. Okay, it's good to do these exercises, basically. Okay, let's talk about some real numbers that we measure on simulators as well as real devices. We work with Google to understand the energy consumption of real workloads that are used by real people, let's say. In this paper, we show that on average use cases on a mobile system, more than 60% of the total system energy is spent on data movement in a processor-centric system. And this is average case. It's not the worst case usage, basically. And the workloads that we examined were Chrome browser, for example, or TensorFlow inference. What else? And video encoding and decoding. So we're kind of exercising all of these right now, wasting a lot of energy. Think about it. Destroying the environment, let's say. Another way of thinking about it is that way, I think. Okay, so we also repeated the study more recently, again with Google, and looked at their edge neural network models on an edge machine learning accelerator, the HTPU at the time. And we found out that the problem is even worse. In fact, more than 90% of total system energy is spent on memory in large machine learning models. I'm going to talk about this a little bit later as well, but just to give you an idea over here, for example, at the time, these are commercial edge neural network models executing on an HTPU. We find out that, especially in the larger ones, most of the energy is spent on off-chip interconnect and off-chip DRAM. And if you actually take a memory-centric approach, which I will describe later on, you can reduce it by about 5x or so on those things. Okay, so basically, I think hopefully I've convinced you that I could give you lots and lots and lots of data, and that will be a full lecture, which is also interesting because people have quantified this problem many times, except these are the more recent results with actually some workloads that are intensive. Essentially, the problem is processing of data is performed far away from the data. And if you want to actually fundamentally solve this problem, you need to take a different approach, which is what we argue for, which is a more data-centric computation paradigm. We want to enable computation with minimal data movement. To be able to do that, you want to really compute where data resides. I call it where it makes sense, in other words, right? If your goal is this, what you're doing today is not making sense because you're moving data a lot, right? So we would like to enable computation capability everywhere in the end. And there are many places we could do it. Today, we're restricting ourselves to a very small fraction of this SRAM-dominated chiplet. And you can scale it. It'll still be the same. But there are other places, like many parts of this is idle because there are huge caches over here, and they're not doing computation. They're just serving the compute units. There's DRAM. There's storage. There's sensors. These are actually huge, right? This is darkness that no one thinks about. It's good to think about that. Maybe we'll have some lectures on storage, but actually, there a lot of things can be done here. Today, we're doing nothing. It's a bit sad, right? If you think about what we're losing is we're losing energy. We're losing performance. We're losing the huge bit-level parallelism that exists in these places, right? There's huge amounts of bit-level parallelism, right? Tera and terabits, actually, if you add all of these things together. All of those bits can be doing computation. Why are we restricting ourselves to here, even from a performance perspective? Maybe we don't need all of those caches. Maybe all of these bits should be computing. And then maybe you don't need that much locality also if you're orchestrating the system that way. Okay, so we're not going to do exactly that in the remaining part of this lecture, but we're going to treat memory as an accelerator. Today, we're actually very good at designing lots of accelerators, but we would like to put some accelerators on the memory side as well. That's the idea that we're going to look at in the rest of the lecture, but I'm going to motivate a little bit more also. So basically, this is a very high-level slide that talks about this accelerator-based near memory or processing in memory, let's say. So you still have a processor. It executes the application. It sends tasks or queries to the memory devices. We're going to focus a lot on main memory and some storage today. And basically, if the main memory or storage is capable of executing that instruction, that query could be an instruction, it could be a function, it could be the entire application offloaded. This does its job and returns the results. It looks nice and it's easier depicted than done, right? Because there are many questions over here. How do you design the memory that can compute? There are a lot of interesting approaches over here. We're going to cover some of them. How do you design the controllers that can compute? How do you design the processors and communication units that can enable this? And maybe how do you simplify the processor once you actually do computation capability in all of these other places? How do you design the software and hardware interfaces to enable this? What is the granularity of computation? How do you offload things? How do you design the system, software, compiles, and languages to make this easier, for example, for people or most people? And then also, how do you map your algorithms to the computation substrate over here? Because the computation substrate could be quite different or similar, but still on the other side of the processor, right? And I think this is one of my favorites over here, theoretical foundations. If you think about how many people have taken a computer science theory course here? Probably not many people. Kind of, yes. So when you quantify the algorithmic complexity, in other way, it could be called algorithmic complexity. So the way we quantify the complexity of algorithms, which should ideally correspond to the execution time a little bit at least, or cost of the algorithm, is by counting operations, right? Big O notation, big theta notation. If you're familiar with this, these are basically counting operations. How many adds do you do? Well, maybe we don't care about that, right? That's a very compute-centric theory of computation today. So this is how ingrained in our thinking is this compute-centric paradigm. Whereas if you think about the data-centric paradigm or memory-centric paradigm, maybe I don't really care about the number of operations I do, right? Or maybe that's a piece of the puzzle. What I really care about maybe data moments, right? If what I told you is true so far, and it is true actually. Okay, so basically this is an exciting cross-stack problem. There are people working on a lot of these areas. And the good news is there are some machines right now that can do some of this at least. Maybe not exactly envisioned, but people are making progress. Okay, I should also say that this is not a new idea. This is a really old idea. Whenever you think about ideas, there are a lot of smart people who have lived through this world, and they may have had similar ideas. It's good to think about that. And some people in the 1960s thought about this. This is the oldest paper I could find. If you find other papers, I'd be very interested in looking at. These papers, this one and the next one, they talk about basically putting logic near memory. So this is processing near memory. And people have looked at this multiple times. Why is it interesting today? Like, why should we look at it today? Like, why are we talking about it? Today, I have much more evidence, because when I was giving this lecture like 10 years ago, we didn't have these memory-centric computers, PIM machines. But now I can talk about it much more, let's say, confidently. I was confident before, too. Okay, but basically, I think today we have nowhere to escape. I've already given you the application and system perspective, right? I've already said all of these. Basically, we're very energy limited. Data moment dominates computation energy, and we want performance, energy, and sustainability today. If you want all of these at the same time, you really need to minimize data moment, essentially. Let's talk about memory technology problems. This is also very interesting because we're having a lot of difficulties with memory technology today. This was not true in the past as much, but now we actually have a lot of issues. I'm going to give you a detour into the technology side. We may actually have some more lectures on this topic later on. But essentially, technology scaling is not going well. As you want to increase the size of memory, increase the capacity, you want to reduce the size of cells. Once you reduce the size of cells, they become unreliable. There's a lot of noise that happens. And because of this noise, your reliability reduces, and you cannot scale the energy, and as well as performance as well. So the solution to this is really demanding intelligence. I'm going to give you some examples of that. And then there are emerging technologies, which are interesting, that can enable some new functions in memory that are relatively new, that were not there before, let's say, in 1960s as much. Actually, they were there, but they were not considered as much. That's very interesting also. Like, a lot of these technologies that we consider today as new are actually old technologies that have, let's say, for example, phase change memory, that were improved over many decades so that they could be enabled. But then there are some integration technologies that we actually have come to, like 3D integration, hybrid bonding, etc., because of the improvement in technology that can enable some new functions as well. Okay, basically, we're squeezed in the middle today. Does that make sense? Okay, so let me give you examples. So to understand these technology scaling issues, we've done a lot of work. I'm going to give you examples from our work. We built this infrastructure. I don't know, some people are over here at Tesseract. I can see his hat over there. Ismail has worked on this a lot. These are our DRAM testing infrastructures, some of them. And the goal here is to have FPGAs, and these FPGAs can be programmable, and they test memory chips. And this is actually the original infrastructure that we built in 2011. You can see that it's kind of makeshift. And we wrote a lot of papers on it. These are the infrastructures. They're open source. We may have some more lectures later on. But basically, these infrastructures enable you to discover and understand and analyze different types of problems. And one of the issues is RowHammer. I'm going to go through this relatively quickly. Basically, you can predictably induce errors in most DRAM memory chips, actually all of them today, assuming you don't have any, let's say, solutions. So people make pictures like this. So it's hammering memory. You don't do it, of course, that way. The way you hammer memory is actually you activate one row. So this is a DRAM subarray, or you can think of it as a DRAM bank. It's a two-dimensional array of cells. If you want to access one bit in one of the rows, you need to activate that word line, which actually connects the bit lines of each cell to the sense amplifier so that you can read the bit line. You can sense it. You don't need to know a lot of details over here yet. But essentially, if you activate this word line, you can read data. Now, if you want to read some other row, you precharge the bank or subarray and basically deactivate the word line, apply low voltage to it. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, or activate precharge, activate precharge, activate precharge, which is valid in DRAM, it turns out some cells that are adjacent, physically adjacent to this row, get corrupt. You basically, the reason is cells are too close to each other and cells are too small. They store some charge. And if you do repeated activation of an adjacent row, their charge gets affected. They leak charge little by little. And if you actually do these activations enough times before the cells get refreshed, you corrupt the data because their charge gets depleted. Make sense? So this is the RowHammer problem, essentially. And this should not be happening. The fact that you're accessing memory should not change the charge level of things that are around you. Right? That's the idea. But today, actually, this happens. So as technology scaling becomes worse, meaning cells become smaller and closer to each other, the number of activations you need to do to induce a bit flip reduces significantly. So we have shown experimentally over, let's say, 10 years, there is a 100x reduction, meaning that you can induce these bit flips really easily. Even benign applications that sometimes access a row many times can cause these bit flips. So this could be not just a security issue, but a robustness issue. Okay, this is also a security issue. A lot of people have picked up on it and showing that if you actually have a bit flip, you can exploit it, and you can do a lot of bad things, which I'm not going to talk about, but maybe we'll have a lecture later on. So that's our original paper. More recently, we've shown that the problem is actually much worse. Again, using this infrastructure, we've discovered another phenomenon, which is row press. Hao Song is sitting in the back. He is the first author. And we analyzed this. And this basically shows that you don't need to activate at the maximal rate to a single row to get bit flips. If you actually activate a row and wait for some time, keep the row active, this actually causes disturbance in adjacent rows. And if you do that, you can actually reduce the number of activations needed to induce a bit flip by 1 to 2 orders of magnitude, which is also fascinating. This is a different read disturbance mechanism. So why am I telling you this? Because these disturbance mechanisms are going to come in more and more as technology scales. And the solution to this is you really need to have some sort of intelligence in the memory controller. We actually argued that from the get-go. In our original paper, we said that the solution to this should be architectural, because all of the other solutions, like device circuit level, they're not there yet. It's going to be expensive. And this is one of the papers that we wrote describing that sort of solution. And 10 years later, the good news is industry is following. They're not, actually, they tried a little bit and they didn't get it right over time, but they're trying to get it right at least. And this is a paper that was written by SK Hynix in 2023 that showed that essentially they built a memory controller inside the DRAM chip to solve this problem. So now you have the solution at a high level. It's an intelligent memory controller, slightly. At a high level, basically, you have, for each row, you have some activation counter. And the DRAM chip internally increments the activation counters based on the number of activations you do. And if the activation count is greater than some threshold, they decide to take some preventive action, like refreshing adjacent rows, for example. I don't want to go into the solutions in detail. We may have a lecture later on. But the point is, now we have intelligent controllers in DRAM chips. And this was more recently standardized by JIDEC. It's called per row activation counters, which is a step in a right direction. If you think about this, a more memory-centric solution, right? It's not a processor-centric solution, because people try to solve this problem on the processor side in the memory controller. You could do that, but it's a bit difficult. If you actually do this in the memory side and give some autonomy to memory, you can actually do much better. I'm not going to talk about that, but we have better solutions than this called the self-managing DRAM that Atabak presented at Micro. We might talk about that later. The question in my mind is, are solutions good? Basically, can you prevent all the bit flips? And I don't think that's easy to solve. So we actually analyzed these solutions in our recent papers. This was at HPC and proposed better solutions. I'm not going to talk about details, but there are better solutions out there. And I believe there are better solutions to come, as well as there are more problems to come. So in fact, in my opinion, we're scratching the surface. This sort of bit flips are going to become worse and worse, and we need more and more intelligent controllers. Now, as you keep adding intelligent controllers, why not also add computation in those intelligent controllers? For example, for each row in memory, if you have some activation counter, why not add some metadata for each row? And that metadata can be useful for programs to exploit potentially, right? They could actually enable computation capability with some metadata next to each row. We're not there yet. The mindset is not fully there. This requires some more changes. Okay, so a couple of things I think that's interesting. We found out that RowHammer, if you keep hammering a row many days, the number of activations you need to do to induce a bit flip reduces. So these sort of effects need to be examined more. There's a paper on that by Giray. And more recently, we have presented a paper at HPCA led by Atabak again called variable read disturbance, which shows that the read disturbance threshold, the number of activations you need to do to induce a bit flip, changes randomly, unpredictably over time. So if you do the testing to figure out how many how many activations you need to do to induce a bit flip for this row, that changes over time as you keep testing. So how do you actually, in the presence of this, accurately identify this? This calls for an even more intelligent memory controller than what is there today. And there could be other solutions to this, and you can talk to Tesseract about that. And that's the paper. So I think this is a very fascinating thing. And you can say, OK, what about emerging technologies? Maybe we should stop DRAM. I don't think we should stop DRAM. We should look at new ways of organizing DRAM. There's like 3D DRAM, for example, that's becoming interesting. I think it needs to be examined. But there are other memory technologies also, like phase change memory, STT-MRAM, and we've done some work in this area. The problem is these technologies all have some problems similar to this. And as they scale to smaller technology nodes, problems like this are going to appear: read disturbance, write disturbance, etc. So you need intelligent controls actually to fix these problems, regardless of the technology you have. My favorite example is flash memory. We may have a lecture on flash memory, although we have only 3 approximately lectures, as you know. In flash memory is a very interesting technology. Like, it was an emerging technology for many, many decades. At some point, it emerged because people found good applications to it. But it's a terrible technology if you think about it. It doesn't work. Meaning, when you actually manufacture the bits, they store some voltage levels. But to make it work, you really need an intelligent controller. The intelligent controller needs to program these voltages carefully so that you don't get these bit flips. If you learn about flash memory, you'll know what I mean. But essentially, all of the memory technologies have this sort of problem. DRAM is a bit lucky, actually. DRAM has been considered the perfect memory technology, and that's why it has been dominant for many, many decades. Except we're noticing that as it scales to very small node sizes, it's not as perfect. OK, so that's why I think this is our lab. Thanks to Ismail, these pictures are here. He took these pictures. This is essentially, I think of this as laboratory for understanding memory and maybe discovering more issues like this. So we do a lot of work in this FPGA lab, and these are some of the memory chips, as you can see. Hopefully, they're labeled correctly. OK, so the read disturbance is very interesting, and there are sessions now in HPCA, ASPLOS, and coming up at ISCA that talk about this. One of them is our paper on PodHammer, which is actually relevant to later parts of this lecture also, but I may talk about it. And it's not only read disturbance, I should say. Read disturbance is very interesting. But the reason we built this infrastructure that I showed you, or earlier versions of this lab or discovery lab, is so that we can actually characterize the data retention. So if you think about DRAM is charge-based memory. If you actually keep the data over there and don't refresh it, you lose charge. And we wanted to understand how bad of a problem this is as you scale the technology. And that's actually a pretty bad problem. But you discover other problems as you actually build this sort of infrastructure and ask questions, right? What else is wrong, potentially? And I think there's more to come. So this is fascinating. But the detour I took was to motivate, actually, what is coming next. Any questions so far? I feel like I spoke a lot, but hopefully it's clear. OK. OK, so if you have intelligence on the memory side, maybe you can do more. Right? And now we're going to talk about doing more, essentially, which is doing actually computation in memory as opposed to keeping memory working. And for this, I'm going to define a terminology, and we're going to examine 2 different types of doing this. And I think there are only 2 different types. If you come up with a new one, let me know. But essentially, processing near memory is what we're doing today. You have logic, you have memory. You design them completely separately. Any kind of memory is designed separately from logic, actually. Logic, you do some computation logic, and memory has a memory design process. In some cases, fabrication processes are completely different also, like DRAM, for example, or flash. Right? But normally, you have different design processes, different verification processes, different maybe fabrication processes, etc. The question is, where do you place the logic? Do you put it far, like we do today? Do you put it even farther? You could. Do you put it closer and closer? Maybe design the logic inside the DRAM chip, for example, next to each bank. You still have memory that's different from logic. They're designed separately, right? But they're closer to each other in processing near memory, such that the downsides of data movement is alleviated. That's the idea of processing near memory. Get closer and closer. Processing using memory is fundamentally different. Logic, memory, again, forget about logic. Doesn't exist. I have this memory I've designed. I can exploit the analog operational properties of this memory to do computation. This is fascinating. And we're going to show you some examples of this, because all memory has some sort of analog operational properties that can enable computation, different types of computation. But you can see that this is completely different. Right? Now you forgot the logic. And this is a different way of thinking about algorithms also. So in the end, processing using memory is very efficient because you're exploiting the memory substrate to do the computation. You're not moving data as much. You can exploit the huge bit level parallelism, so there's a lot of parallelism. But processing near memory can be much more capable in terms of the operations because you're designing logic. You could design the logic as you design today, just put it next to memory. Maybe if you have a 3D stacking technology, you can have a very sophisticated processor in the logic layer, and you can have memory on top of it. Right? So a capability of processing near memory is better, but the efficiency may be lower because it doesn't reduce the data moment as much. In the end, I think we need to explore both and combine both of these things in the best ways. But there's a lot of, I think, creativity that needs to go into both of them. OK, so this is a slide that shows where you could do processing near memory. For example, if you have 3D stacked memory, you could do processing inside the logic layer. Or you could do processing near bank. Whereas processing using DRAM is restricted to the arrays, for example, as I will show you soon. You basically take advantage of the analog operation over here. OK, but before we delve into that, today, there are a lot of prototypes that show processing near memory. Not all of them are 3D stacked, but 3D stacking actually is a very nice technology, in my opinion, and there are better integration technologies that enable things. You have logic layer and you have memory layers on top of that, and they're connected through some sort of interconnect. They could be large through silicon vias, they could be smaller interconnects through hybrid bonding, and in better integration technologies, they could be actually vias that are really small, let's say. So the density of this interconnect determines how much bandwidth you have between the memory layers and the logic layers. And also the fabrication as well as energy characteristics depends on how much energy you spend. So that's good. This doesn't exist as much yet, but it actually exists, except it's not at least productized. But people have productized, for example, this, and we have a lot of work on this. I'm not going to talk about that, but there is this company called UpMem in France. They built DDR4 DRAM, and inside, next to each bank in the DRAM, you have a processor. And this processor is a multiple instruction, multiple data, multi-threaded processor. That's general purpose. It can do any operation, essentially, except it can do some things better than others. OK, so this is actually very interesting. And you can actually buy this and program it if you're interested in it. And if you have some ideas, we can discuss that also. And then this is commercially available. At least it was commercially available until recently. And then there are other prototypes that are developed by SK Hynix, Samsung, more Samsung, Alibaba. And these are more specialized DRAM chips where next to each bank or next to a set of banks, you have some acceleration logic, like matrix multiplication or multiply and accumulate support. So you can actually offload simple matrix operations, for example, to the chip. And their goal is to actually accelerate neural networks or recommendation systems, etc. This is a bit different. This is near memory still, but here the computation is done in an FPGA on the board. And then there are a lot of memory chips next to that FPGA. So you can see that there are different types of processing near memory. The good news is there are also a lot of experimental chips and startups that are doing things like this. But this is near memory, so it's near term, meaning it's easier to do this because we're not, let's say, exploiting memory to do something more analog and less reliable. So if you think about processing using memory, it's going to be less reliable. Whereas this is, we know how to design logic reliably, and you can do that inside the memory chip. Even in a fabrication process like DRAM, you can do that. OK, and then there are also interesting things like CXL, which is a Compute Express Link, which enables interfaces from a compute unit, like a processor, such that you can offload computation to somewhere else. And people have done that. This is another paper from SK Hynix that shows that they can offload computation to a near memory FPGA, for example. And we have some works in this area also, but I'm not going to talk about that. OK, now let me give you some research results. So when we first started looking at processing in memory, and especially processing near memory, one of the things that we were quite excited about is the technology, which is 3D stacking in this particular case. I've already kind of given you the technology. You have a logic layer, and you have memory layers, and you can fabricate that nice. And we believed in the technology. At the time, the technology was not that mature. We're talking about 2012 or so. And there was hybrid memory cube, which is dead today. But there's HBM, which is actually somewhat similar, except it does some things better, some things worse, in my opinion. Like the interface is worse, I think. But anyway, if you can stack logic and memory on top of each other with some connectivity, high bandwidth, low latency, low energy, can you do something about it? Like, what can you accelerate? And what we looked at the time was especially graph processing applications. Even though the system is quite general, as you will see, we wanted to accelerate graph processing applications. And our vision was you have a host processor that offloads graph computation to an accelerator that looks like this. So what is this accelerator? It's actually a distributed system of these cubes. Let's call these cubes. Each cube has a logic layer. In the logic layer, you have an array of processors that are connected to each other. They can communicate with each other. And you have an array of these cubes connected to each other with some topology. Interconnect topology is actually very interesting over here. We'll get back to that in a little bit. But the idea is you offload some graph computation. You partition your graph on top of these cubes. And in each cube, you partition your graph on top of the memory that belongs to each processor. Okay? And if you want to do some computation on a graph node, what you do is you don't move the data to the function. You move the function to the data. So if a processor wants to do some update on a graph node that belongs to this processor, it sends a message to this processor saying, update this node, and here's the update you need to do. Now, if you do that, you move the data less, you move the functions more. But it turns out moving the data less is a good thing in this case. That's the idea. So this is programmed using remote procedure calls, which is actually a distributed system programming model that's used in data centers today. It's a full system work, so I'm not going to go into every single detail over here. But the cores over here are very simple in-order cores. They communicate via this message passing. And the reason they're very simple in-order cores is, first, you don't need a lot of latency tolerance. Second, you cannot afford to put complicated cores over here due to thermal problems that you have and due to area budget that you have. So it's good to think about that. So there's still thermal problems. The 3D stacking actually exacerbates this thermal problem, which is not a solved issue, but you have to take that as a constraint. And that's one of the reasons why you cannot stack a lot of memory also, actually. But even then, we still need to have prefetching mechanisms because the latency tolerance of an in-order core is not good. So a lot of the prefetching mechanisms that we discussed are still applicable over here. Now, let me give you some example results very quickly. This is a paper that you can read. It's 10 years ago. It was rejected twice before it was accepted to ISCA. But what matters is what happens afterwards, not being rejected, not when it's rejected. Of course, it doesn't feel good. But basically, if you look at this system, Tesseract system, it doesn't look like any of the existing systems at the time or today, because processing and memory are coupled to each other, right? And then you have a distributed system of these processing near memory engines. And you get a lot of bandwidth for 512 cores over here. Now, if you actually, we should have looked at machine learning over here. If you actually squint at it, this looks like a GPU, machine learning accelerator, essentially. This is how things are designed today. If you go to industry and design machine learning accelerators, you have a distributed system of GPUs connected to each other. Each GPU has an HBM next to it, except GPU is still a bit far away from the HBM. It's not next to each other, right? It's not near memory processing, I would say, but it's nearer memory processing than what you may think about when you think about CPUs, let's say. But it's actually similar in concept to that sort of machine learning accelerator, but we're going a little bit farther. Right? Okay, and we didn't really specialize a lot for graph processing in this particular case. It's really an in-order core. Right? Okay, but basically you get significant performance improvements on average across 5 graph processing algorithms. Numbers are large, as you can see, but later works improved on this work. Many works exist actually that improve on this work, and that takes the number to 100x or so. I stopped following at some point, but people improved a lot of stuff over here, specializes, etc. Energy reduction is also significant, and again, later works improved on this. So basically, you improve performance as well as energy, assuming the collective works until 2022 or so. You improve performance of graph processing by 100x. You reduce energy by 100x. That sounds good, right? It's not a trade-off anymore. Okay, if you're interested, this is the paper. And these good folks who rejected our paper multiple times also decided to invite it to 50 years of ISCA. Maybe they're not the exact same folks, but so they found value after it was accepted clearly over time. So if your work gets rejected, don't worry, because believe in the work. And if it actually is doing something good, it may have a lot of impact down the road. Right? I have a lot of these stories. I can give you one over here. Okay, so there's more you can do if you actually rethink the system and formulate your algorithms in a way that's more amenable to acceleration using processing in memory and also processing using memory, as we will see, you can actually get a lot more performance improvement. This is a collaborative work that we've done where you actually specify an instruction set architecture that's set-based. You basically operate on sets, set union, set intersection, and then you express your graph algorithms, for example, PageRank, etc., in terms of set union, set intersection. These are very simple operations, bitwise operations on sets. And maybe even a compiler can actually help you over here to compile applications or algorithms into set-based operations. And then you can actually accelerate those set-based operations on the near memory side as well as using memory side. This will become more clear when we talk about using memory, because we will see a lot of bitwise operations over there. But for near memory, this is also very good. So I think it's good to rethink the system from algorithms to ISA compilers to actually how to see how we can best take advantage of processing in memory systems. This is one paper that does that, I think. Any questions? I'm giving you a broad stroke, so hopefully it's interesting. Okay, let's talk about machine learning inference. There's another work that we did that I mentioned earlier with Google. And we analyzed on Google Edge TPU different neural network models at the time used by Google. These are commercial neural network models. So unfortunately, none of this is open source. Google didn't let us open source this one. But basically, we found out that on these machine learning models, you have a huge diversity, variation in terms of the characteristics of the layers of the model. For example, some layers have huge arithmetic intensity. You do 10,000 floating point operations per byte. This sounds good for doing, bringing something into the cache and do a lot of operations, and you amortize the energy cost of bringing data. But then there are some layers that are actually exactly the opposite. You do very little operations in terms of on a single byte that you bring. And then there's a parameter footprint over here. Here, the parameter footprint is very large. Here, it's relatively small. So basically, the question is, if you have this sort of variation, what kind of a system do you design? When I see this sort of huge variation, heterogeneity come to mind. Basically, design different accelerators to cater for these different types of layers. And that's what we're going to do, essentially. And if you actually look at the variation in terms of layer characteristics within each model, you see that different layers have huge variation in terms of multiply and accumulate operation counts or arithmetic intensity, flops per byte. So basically, people normally design these TPUs or accelerators as a monolithic accelerator. They try to cater to all of these different characteristics at once. And as a result, this accelerator becomes, again, a monster, meaning it becomes big. Because you need to have a huge, let's say, parameter cache. You need to have many units over here to cater for many different things in the worst case, let's say. Of course, they're not designed for the worst case, but that's the idea. So our idea is basically, instead of doing that, have, let's say, n different type of accelerators. In this case, n equals 3. One of them is compute-centric, that caters for these layers that are actually very compute intensive. And the others are data-centric. These are actually accelerators in the logic layer of 3D stacked DRAM. And they're designed for different types of data flows, et cetera, based on the characteristics of the layers. And have a runtime system that distributes the layers that you're executing to different accelerators. And we show that in this work, if you can actually do this statically or dynamically, if you know the families. How do you actually decide which one, what layer goes where, or which accelerator? We have some clustering mechanism to do that. There's more work to be done in this area, by the way. The schedule is actually really important over here, in my opinion. And also, how do you exploit the parallelism that you have over here with this sort of scheduler is also important. But basically, we have an algorithm to decide what goes to compute-centric accelerators and what goes to data-centric accelerators. And in the end, we show that you can reduce energy consumption by about 3x compared to the baseline Edge TPU. You can see that the ones that gain the most are over here, large models. And you can also improve throughput compared to the baseline Edge TPU. And it turns out, here I don't have the results, but it turns out if you look at the area cost of those 3 accelerators combined together, it's smaller than the area cost of the monolithic accelerator. Clearly, the complexity is higher. Right? Monolithic accelerator is not complex because you design one thing. But if you actually design 3 things, the total area cost, additional area cost is smaller, if that means anything. But I think this is evidence to show that existing systems are over-provisioned to cater to data-intensive, to cater to everything. Whereas if you actually do computation in different places, you can reduce the area cost that you have. Complexity increases, no question about that. And you need to actually program it, etc. OK, let me quickly go over a couple of things, and then we're going to take a break. So there's more work in this area that we have done. This paper that I mentioned, this is actually the first paper that we wrote with Google. If you're interested, you can take a look at that. If this were a longer lecture, I would talk about that. We have been accelerating bioinformatics workloads, especially. As I said, this is a huge data-intensive problem, and we have looked at 3D stacking techniques for this. And more recently, we've been looking at storage. And this is Nika's work over there. Nika is in the back. She can talk more about these works, but I'll mention one of these relatively quickly because these are very large data sets in genomics. For example, you want to compare the sequence genome or query genome of someone to a reference genome, you need to go through a lot of data. And if you want to do this on many, many genomes, if you basically, for example, I took a sample over here, and I want to understand what is lurking here, right? What kind of viruses, what kind of bacteria. To be able to understand what's here, I may need to compare it to databases of size hundreds of terabytes, right? Many, many different genomes. That's actually a very interesting comparison. If you could do it in a storage, you basically need to go to storage. Gigabytes is not enough, terabytes is not enough, hundreds of terabytes is what you want. I'll give you one example with GenStore over here. This is Nika's work in ASPOS 2022. But basically, the idea is if you want to do genome sequence analysis, what you do today is you bring a lot of data, which is genomes, let's say, to a computation. It could be a CPU, GPU, accelerator, whatever. But this clearly has a lot of computation overhead because the computation complexity of edit distance computation, which is one way of analyzing the genome, is high. It's usually done using dynamic programming. You can do a lot of actually acceleration and filtering techniques, etc. But if you do it, let's say, not so smartly, you have a lot of computation overhead. But you also have a lot of data movement overhead. Okay, now people do smart things. People do actually a lot of heuristics, accelerators, filtering mechanisms to reduce the computation overhead. And actually, they do in-memory processing, potentially. This reduces the computation overhead and a little bit of the data movement overhead, but this doesn't do anything to the data movement overhead from the storage system. There's still a lot of data that gets moved from storage. In fact, this exacerbates the data movement overhead. If you think about it, if you reduce the computation overhead with smart techniques, including processing in memory, let's say, in main memory, the data movement overhead from the storage system becomes a bigger bottleneck, right? That's Amdahl's law for you. Okay, so basically the idea in this work is to filter the reads, or reads are sequences or fragments of a genome that don't require alignment. Add some smartness, add some computation capability into the storage system so that you do simple things over there, so that only very little amount of things that really require the processing capability get moved over here. So for example, what can you filter? If part of the genome is exactly matching a reference genome, that's very easy to detect, right? It's an exact match detector. And that way, you don't need to move things that are exactly matching all the way here to do a very simple computation. Make sense? If part of the genome that you sequenced is not matching, and you can detect that very easily with simple techniques on the storage system, you don't need to move those also. So what you really need to move things, move to the computation units are things that you cannot decide easily. So that's the idea. This is one way of partitioning the work. Okay, and this reduces the computation overhead as well as data movement overhead, and it gives significant speed up and energy improvements at the same time. Okay, so if you're interested, talk to Nika. This is her more recent work, which is even more involved, but I don't have time to talk about that. But if you want to see more examples, we have this primer paper that talks about a lot of near memory processing examples. Before I take a break, I will mention that since everybody is interested in large language models are also bottlenecked by memory. And we have some recent works that talk about how to design, let's say, processing in memory systems that accelerate large language models. Again, if you look over here, this is a PAPI system. Again, I will not go into a lot of detail over here, but if you partition the computation smartly across high performance processing units, GPUs, and some processing in memory engines that have a lot of computation capability to accelerate fully connected layers, and also some other processing in memory systems that can cater for low arithmetic intensity parts of your system, attention, for example, attention computation layers. They require actually large capacity and also some computation, but not as much computation as here or there. But you need large capacity. And if you design a system like this, you get significant performance as well as energy improvements in terms of LLM inference. I think this is where I should stop because we're already over time. Any questions? We've covered processing near memory. As I said, I want this to be an overview as opposed to like going every nitty-gritty detail of everything talked about. Clearly, that's not going to be possible because I covered a lot of works over here. But hopefully, this gives you a perspective. So let's take a break, let's say until, I don't know, okay, 15:17. Let's be back at that time, and then we're going to cover, let's say, in my opinion, a more fascinating part, although I'm fascinated by processing near memory with the creativity that people come up with new logic. But we're going to look at an even more fascinating thing, a more difficult thing also. Coming up with the next crossing.
Yes.
There's more to do.
I think there is, yes. But I think
Programming is good.
I think there are limitations when it comes to how we try to use limitations for processing using them. There are limitations on how data moves.
Yeah, sure.
You know,
We need to fix those.
row-wise. So trying to think how we can input some cells
That sounds good.
in a specific regions, for example, interconnect process, and then have a way to kind of propagate movement between, for example, to do similar processing using memory operations, but
I think that's good actually. Even if it incurs some area overhead, I think it's good to explore because not many people have explored this.
yes, but let's find the details of how to the cells interconnect in a way that's efficient and still keeping capacity.
Still keeping capacity not really important.
To an
I think you
extent.
can quantify how much lose.
To an extent, yes.
Could be dedicated something.
Exactly.
Could be dedicated to computation.
Yes. But eliminating the substrate for computation is also and not entirely, but to an extent also because we're relying on it. If we keep relying on it and have an access kind of nature to the memory, it's still not processing memory. We're not using memory. More processing using memory.
It may be okay to lose some capacity. That's a lot of performance.
You could have
It's good to explore that trade-off space. That's not been explored.
You could have hybrid dies as well. Dies that are completely memory, dies that are
That's what we're saying. That's what we're talking about. Why we're not saying DRAM architecture. Completely. I mean, it's difficult to integrate.
But then later we're doing storage and
but it's more interesting to something in the basic where we're doing processing near
One of these sections.
not that it's it's I think in the mid it's like trying to push
before
something
It's
that's
easier
also
to-
using that.
Using is harder, but I think it's good to look at using as a, like, what do I change?
Yes, we really said that.
I like this.
Yes.
There would be more work in that
Because it
area.
was the same text.
We have 2 weeks since the brainstorm, so we'll come up with something.
section. That's the section.
I thought you were going to say we have 2 weeks until the deadline.
We don't have 2 weeks. You
Then afterwards it goes
You were talking about
in storage engine and
Was there a
somehow it
brainstorming
explains this again.
no, a brainstorm between me and Carlos
Okay,
in a specific lab that we take together. There were stars brainstorm.
I heard it was a keyboard. But I had to go with. No, I setting up a box at home. So I arrived there 6, 7 p.m. I don't know. I think I wouldn't expect it. The everything was fine. Okay, is there a number of how long it took from the service in the first until the service in the last?
I took it from Cop.
Okay.
Yeah,
That's also very true. More relevant.
that's true.
Yes, that is true.
Like almost so so many things like
That and the scheduling. CCTs and all the scheduling. Scheduling is kind of off topic.
Do you know that CCD is
Yeah.
kind of it's not in the ground for could be. Oh, yeah.
yogurt or protein drinks and kind of reasonable, but everything else.
Oh, no, we already have protein.
Usually coming back at 15.
Yeah.
Oh, 17.
Just have like some more protein.
Extra protein.
Sorry.
I said extra protein.
Almost freeze. Okay. I mean, similar to here.
Actually, while here it was really good, here it was not.
I mean, during Easter it rained like Easter Sunday.
This was great. And then after
Okay.
Easter, it got worse. I think here it was great. It was opposite. Because when I came back here, it got great in Greece, and here was freezing up. Unfortunately. It's fine because I saw. I was not sure what the camera is.
Everything was like usual.
We didn't do enough.
No, but I mean like Greece was like usual or did it change? Yeah, we kind of, I think we managed to kind of want to everyone to meet. Because I think my grandparents are so managed to.
So you define the center. Yes.
All good? Okay. Okay, I think we can get started. Okay, that was a quick introduction to why we do processing in memory and some processing near memory techniques. There's a lot more actually. I may give you some examples. There are a lot of backup slides, so if you can also take a look at them. But let's move to processing using memory, which is a fundamentally different approach to approaching processing in memory. I'll especially look at processing using DRAM in the rest of this lecture. But you can do processing using SRAM, processing using flash, processing using emerging technologies, PCM, RRAM, embedded DRAM, etc. And they all are slightly different, but some fundamental principles apply. And I'm going to show you some at least two types of primitive operations that can enable data copying as well as computation. So basically, using DRAM, using the analog computation capability of the memory substrate, we can support bulk bitwise copying, initialization and zeroing, which is a special case of copying, many different bulk bitwise operations, and or not majority, nor NAND. I will show you examples. We can generate two random numbers. We can do physical unclonable functions. And if you want to do more complex computation, you can add more logic to do lookup tables. Most of this happens at low cost. You need to change the row decoder circuitry and maybe where you do the computation, etc. And we exploit the analog computation capability that inherently exists in the DRAM structures. And the key idea is really, if you activate multiple rows, you perform computation. If you activate them concurrently, you perform some computation. If you activate them sequentially, in quick sequence, in quick succession, you perform data copy. And that's the idea, basically, we're going to look at. In some other emerging memory technologies, you can also do matrix vector multiplication in the analog domain. I'm not going to talk about that because you don't have a lot of time. But if this was a longer lecture, there would be some slides. I think in the backup slides, I have some of those emerging technologies. And the fascinating thing is, you can see these operations in commodity off-the-shelf DRAM chips. So using the infrastructure that I showed you earlier, you can abuse the timing parameters of DRAM, reduce the timing parameters, and we can see that you can do data copying. You can do bitwise and or not majority NAND nor. Even though DRAM chips, commodity off-the-shelf DRAM chips are not designed for this purpose, nobody advertised them this way, but you can actually do the computation. This is the fascinating part. Yes?
Are these instructions for like bitwise operations extend?
Yes, basically you need to do something like that. I'm going to show you some examples of that, but yes, you will need to, if you want to exploit that, you will need to do that. Okay, and you see significant performance energy improvements. These numbers are out of date, but yeah. Let's start with simple. Let's start with the simplest thing you can do, in my opinion, currently, which is data copying and initialization. So we copy a lot of data in our systems for many reasons. Security is one reason. It's initialization, basically. Whenever you deallocate a page, you initialize it to or you randomize it or set it to 0. And Google, in their paper that I mentioned earlier in 2015, they basically showed that across all of their data center workloads, a huge set of workloads, only these two function calls, memmove and memcopy, occupy 5% of cycles. This is a huge number for two function calls. It's not all of the data movement in the system. It's just data movement that's generated by two function calls. And in that same paper, they said that techniques like what I'm going to describe next, they cite our paper, are going to be more and more important into the future to reduce that sort of data copy cost, because our paper was published earlier than their 2015 paper. Okay, so how do you do data movement today? Again, let's take the hat of a 10-year-old. You're the 10-year-olds. I'm telling you how I do the data movement today. I want to copy this 4 kilobyte page to this 4 kilobyte page. And the way I do it is take it byte by byte, go to the CPU, bring it to the L1, take this byte by byte, go through the CPU, bring it to the L1, do the copy, and write back the destination over there. As a 10-year-old kid, what would you tell me? Okay, somebody said stupid. Yes, probably that's the honest answer of a 10-year-old kid. I agree. Basically, a 10-year-old kid would say, let's just do this. Let's not be stupid. But we are stupid. Okay. Anyway, there are reasons why we're stupid, but that doesn't change the fact that that's stupid, I think. Okay, basically, if you actually do what a 10-year-old kid would naturally probably do without having all of this baggage of how we design systems, you would do it inside the memory. You would basically save latency. You would avoid cache pollution. You would reduce the bandwidth utilization on one of the most important resources that we have in the system today. And you won't cause unwanted data movement. It's not always the best option, but if you had this option, you could actually figure out when you would like to do this. Right? Today, we have no option. Right? That's the problem, basically. The problem is not that we're not doing it all the time here. The problem is we don't have any option other than going through the CPU or the memory controller today. If we had this option, then you can design a system that's probably much better than today. Like, I'm not suggesting replace all of the data movement by doing it inside the memory. Sometimes people get anxious, or you say stupid. Yeah, you can do it sometimes, right? It's an optimization problem. Why not enable options in the system? Right? So we're not extreme in the sense that we're not saying do everything in memory. Enable options. Okay, so if you actually do this inside the memory, you can reduce the, let's say, 1,000 nanoseconds 4 kilobyte page copy cost to 90 nanoseconds unoptimized, and reduce the energy from 3.6 microjoules to 0.04 microjoules. Now let's take a look at how we do it in the best case. So this is a DRAM subarray. You've seen this before. It kind of looks a little bit slightly different, but it's a two-dimensional array of DRAM cells. And this is a row buffer, which is a sense amplifiers. So whenever you actually activate one row, this brings the data into the row buffer, transfers the data, and this row buffer is to let's say, cross-coupled inverters. Each cell over here is a very strong sense amplifier. So the data is captured strongly inside this SRAM type of circuit, essentially. That's step one. You activate row A. Now you captured row A in the sense amplifiers. Now what I'm going to do is to activate row B, which deactivates row A implicitly and connects the sense amplifiers to the destination row cells. Now, if you do that, the data that was captured that's very strong inside the SRAM cells over here drives into the DRAM cells, because these are actually very weak and these are very strong, and you drive the data inside. So by exploiting the chart sharing, this is called chart sharing, by exploiting the chart sharing principles of activating one row and then activating the next row, you bring the data through the row buffer into the destination row. And this is the fastest we could do it. Maybe there are better ways, but without changing the circuitry as much, you can do that. So 2 consecutive activates, negligible hardware cost, and you get significant latency and energy improvements. And I'm going to show you later that you can actually do this by violating the timing parameters. Today's DRAM, there's an activate to activate timing parameter, and DRAM data sheets tell you not to violate that, because that's how you reliably read the data from the second activated row, right? But if you actually violate that parameter and ensure that source and destination are in the same subarray, you can do this copying in existing DRAM chips almost perfectly reliably, as we will see later. Yes?
Is this a pure software?
Which one? No, this is basically exploiting the existing DRAM, right?
Would it be a software implementation or to change this?
Oh, I see. Yes, there needs to be some software changes that you need to do, right? To be able to do this, the source and data rows need to be in the same subarray, right?
Yeah. So
and that allocation, if they're in different subarrays, you won't be able to do this. Exactly. If you need to change your system such that the destination page is allocated in the same subarray. This requires awareness for your memory allocator. So even something as simple as this requires some work in the software stack, and that's an adoption issue.
But it doesn't require any extra hardware.
It doesn't. Well, to be able to do this reliably, you will need some hardware, but you could also. I will talk about that later. You could build an FPGA prototype that could do this, which Atabak did next to you sitting. You can talk to him. That changes the software such that you could do this in existing DRAM chips without changing, let's say, any hardware except for the memory controller. You only need to change the memory controller. Okay, but you don't need to change the DRAM chips. That's the fascinating part. Okay, so you can actually ask a lot of questions. This is a RowClone paper, which was rejected once after it was accepted later. But basically, you can do a lot of questions. Can you do a faster copy? Yes, inter-subarray, across subarrays. I'm not going to talk about these. You can move data at smaller granularities. You don't have to do it at 4 kilobytes, etc. Can you do a better interbank copy across different banks? Yes. But let's talk about computation. Can you do computation? let's say. And let me give you the primitive for computation in DRAM, at least one primitive for computation. Maybe there are others waiting to be discovered. Now I'm showing you 3 DRAM cells. Now we go into a little bit more detail. These are the capacitors in DRAM. These are the access transistors for each capacitor. And these are the word lines, except I'm showing you only 1 bit per word line. And this is the bit line. And this is the sense amplifier. And this is the other end of the sense amplifier. Right. Now, if you imagine 3 of these rows, 3 cells, I'm going to concurrently activate these 3 cells. And imagine this be happening on 4 kilobytes of data, bulk bitwise. And imagine this happening on thousands of subarrays. So you could do this on millions of bits concurrently. Let's do on 1 bit. You concurrently activate these 3 cells, which means that you connect the access transistors to the bit line. Now, they share the capacitors share their charge. In a perfect circuit, if at least 2 cells are charged, you get the charge state at the end. If at least 2 cells are discharged, you get the discharge state at the end. And based on what I just said, logically, this is a bitwise majority function. So basically, the final state that you get on this end of the bit line is really a bitwise majority of the 3 cells. Make sense? And this is the majority inverted, essentially. This is nice, bitwise majority. It's a beautiful function. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you have majority, OR, AND. That's good. What's missing is a NOT, meaning essentially inversion, right? So if you want to be Boolean complete or functionally complete, you just need a majority and a NOT, or AND and NOT, or and NOT, right? Now, that's a bit difficult, but in this paper, we propose that how do you get the NOTs? NOTs is actually already there. If you activate only C, for example, let's give one example, you get the charge state over here, assuming it's charged, and you get the discharge state over here. So actually, the inverted value is over here on the other end of the sense amplifier, except you need to connect it somewhere. And in this paper, we propose an expensive way of connecting it to this subarray. And you can read the paper. So you can actually get the inversion. And if you actually have all of these things, majority, and or an inversion, now you can actually rethink your algorithms to match this. Right? And in this work, we actually looked at databases, also set operations, as we will discuss. You can, in databases, for example, you can do a lot of bitwise operations. If you want to compare, if you want to, for example, find people in a database who are between some age, who make some amount of money, who go to ETH, you can represent all of those things as columns of bits. And then you could do bitwise operations on those entire vectors to actually figure out which ones satisfy all of those properties. Right? So you can do bitwise operations on huge vectors. And some databases are actually designed for that purpose. This is the bit-weaving database. People design these databases to maximize the bitwise operations in the database so that you can actually use sophisticated FPGAs or GPUs for it. We actually port that database to M-bits, and we see significant performance improvements on that and energy improvements. But essentially, if you can rewrite your algorithms to take advantage of these bulk bitwise operations and maximize parallelism, you can actually do a lot. We looked at databases. We looked at set operations, set union, set intersection. People actually design web searches to maximize bitwise operations. There are encryption algorithms, and there's DNA sequence mapping. These are all do a lot of bitwise operations, actually. This paper doesn't cover all of them, but we cover different ones in different papers. So this is the paper, M-bit. So how do you make it more programmable? You asked some good questions earlier. In the M-bit paper, we talk about how to expose it to the ISA, et cetera. It requires changes so that you can actually export these operations to the memory controller clearly. But we have a more, let's say, principled framework to export any operation. So imagine that you want to do matrix multiplication. Right? You express your matrix multiplication using a circuit that looks like this, and or not logic, or convolution, or multiplication, or division, whatever. You can express, you're a hardware designer, and hardware designers are good at expressing things using circuit, right? You can do that, and we take that and convert it to what's called a majority inverter graph. And people have designed actually electronic design automation tools so that they can take advantage of the superconducting logic. This work was done by Nanni De Michele's group at EPFL. We use that to, let's say, optimize this majority inverter graph. And then we convert it to a sequence of commands. Like these are triple row activations, RowClone, et cetera. You need to use RowClone also to be able to do that. Essentially a microprogram that's associated with the operation that you have. We call it bulk bitwise operation. You store it somewhere. Basically, whenever you see this bulk bitwise operation executed by the program, you call this microprogram that's executed in the memory controller. So a compiler or a programmer essentially inserts a block bitwise operation to do block bitwise multiplication, for example, right? It gets shipped to the memory controller, and the memory controller executes this microprogram. This way, you can integrate it into a sequential programming model, as you can see, and a single instruction can unleash a lot of parallelism in memory. So this is one way of taking advantage of these operations. And again, I will not go into details. There's a lot of evaluation in the paper, but you can get significant throughput and energy improvements, as well as overall application and performance improvements compared to existing CPUs and GPUs at the time. Okay, that's SIMDRAM, which is very interesting. So now we are talking about some adoption issues, like this programmability, in my opinion. How do you actually make this more programmable? In more recent work, Geraldo, who just defended his thesis like last week, not a few days ago anymore, he basically developed this MIMDRAM substrate, which solves some of the other problems. I will give you the key idea over here. But basically, one of the issues with this block bitwise operations is you're doing too much. Kind of you have too much parallelism, 4 kilobytes or 8 kilobytes, assuming the row size is 8 kilobytes. But a lot of compilers cannot target 8 kilobytes. Whenever you actually exploit parallelism at the vector level, usually your compilers can target smaller bit widths. For example, at AVX is 512 bits, right? Sometimes even smaller, actually. So one of the issues is if your parallelism doesn't match the parallelism that you have in DRAM, you're wasting a lot of things. You need to pad your data such that you do something useless over here, right? So in this work, the realization is that if you actually enable finer grain operations in DRAM, so if you look at a subarray in DRAM, you can actually, it's partitioned into smaller arrays. So if you look at DRAM, there's a big array bank. It's partitioned into subarrays, smaller arrays. Each subarray is also partitioned into smaller arrays called mats. And the reason for this is so that you can actually have lower latencies and better reliability, etc. I'm not going to go into that. But these subarrays, these mats, are today not accessible individually. So what this work does is it says basically, oh, let's make them accessible individually, such that if you want to only operate on, let's say, these two subarrays, these two mats, let's say 512 bits plus 512 bits, we can do only these. And the way we do it is basically by segmenting the word line. We put some isolation transistors or a way of disconnecting this part of the bit line from this part of the bit line, such that you can do operations over here without doing anything over here. That's the idea. It's not a new idea. It's called fine-grained DRAM. There are many papers. I'm going to mention one of them. But once you do that, you can do one operation over here and maybe some other operation over here. And you can exploit the concurrency of smaller bit width operations across different mats. That's the beauty, right? You can pack essentially multiple instructions operating on different data elements, right? So it's a multiple instruction, multiple data. That's why it's called MIMDRAM. And Atabak has developed sector DRAM, which works nicely, I believe, with this one. It's an example of fine-grained DRAM architecture. Do you agree? Okay. Okay. So this work does more. I will not go into details, but for example, when you actually aggregate data, I believe you cannot do everything just this way. It's good to add some logic over here such that you do some aggregation or reduction. And this work adds some low-cost interconnects for enabling vector reduction. And I think there needs to be, this is a processing near memory example over here. I think there needs to be more added, but that's future work. And then I think one of the big contributions of this work is because you reduce the granularity of the bit width you can operate at inside the DRAM, now you can retarget a compiler, existing compiler, like LLVM in this work, such that you can do automatic vectorization using LLVM of applications that are suitable for it. And you can target these 512-bit, let's say, arrays, mats, and completely transparently to the programmer, you can exploit the parallelism that you can execute in the DRAM. That's the idea over here. Now, you can target an existing compiler. And Geraldo modified the compiler to be able to do this transparently. I will not go into details. You can download his source code and do better. I think this is a good opportunity to do better, in my opinion. Essentially, I believe, I'm not a huge believer in auto-vectorization, but this was an easy thing to do. I think compilers are still not very good at vectorizing automatically. And people need to do some of this, in my opinion. But again, you can cut this part, and the compiler can still do the code scheduling and data mapping to memory and do generation of code such that you can actually do the operations inside the memory using MIMDRAM substrate. And the results are quite impressive. in this case, the results show that if you actually use every single subarray in DRAM to parallelize these vectorizable workloads, you can get huge energy efficiency improvements compared to CPUs and GPUs. And the reason is essentially you put every bit to work, if you think about it. You're not adding a lot of computation overhead. There's no logic, no significant logic added to do the computation. Computation is happening in parallel across many bits at low energy. But if you look at a GPU or a CPU, there's a lot of baggage that is required to enable computation. There's a lot of control overhead, for example, right? There's a lot of overhead in terms of the memory hierarchy, and that doesn't exist over here. You're completely parallelizing it. Again, take it with a grain of salt because these are highly vectorizable workloads, making it work for more, let's say, irregular workloads with higher sparsity, for example. These are open problems that are actually very important, in my opinion, in this area. Make sense? Okay, so in the remaining time, I will give you something that fascinates me, and I think Ismail and maybe other people over here also. Hopefully Atabak too, because he built some infrastructure that shows this. But basically, we're not smoking pot, meaning this hardware actually can do some of this, right? Well, I say this because, for example, when we wrote the MBIT paper in 2015, the first time, one of the reviews said, this is useless. Essentially, that was the gist of the review. So it was rejected 4 times before it got accepted. So we also decided, okay, can we actually do this in real DRAM chips? And we were inspired by a paper from Princeton that it was called Compute DRAM, that initially showed that actually there is some capability in DRAM chips. So Atabak built on that work and basically provided this end-to-end FPGA-based framework where he essentially modified the software and the hardware such that an application can do a page copy call that gets mapped nicely to the subarrays in DRAM, such that it gets translated into the memory controller, and the memory controller does the copy by violating the timing parameters, such that the source and the source page gets copied to the destination page in DRAM. This requires changes to the operating system, changes to the application a little bit, and clearly changes to the memory controller. But this is a substrate that he'd be happy to help you with. I'm putting words into his mouth right now, but if you're interested in experimenting, it's not an easy system to experiment with, but still, you can do it essentially. So this doesn't use any non-commodity parts. It's just violates the timing parameters, and there's a bunch of changes to system software and slightly applications. Okay, so this is all open source. Even if you don't have access to Atabak, you can actually have access to the open source GitHub as long as you can go to the website. And Atabak has some results in the paper showing that this is hugely improving the throughput. And the reason throughput improvements are huge over here, these are micro benchmarks, but still, these are huge throughput improvements, is because the processor that you have in the FPGA that executes the program is actually a very wimpy processor. It's like 50 megahertz, right? So it has no latency tolerance mechanism. So if you actually have a very powerful processor over here, it will have some latency tolerance mechanisms, and you will not get as much improvement, but you will still get a lot of improvement. So it's good to think about this. This is a prototype to show that you can do this end-to-end, and maybe other people can develop on top of this such that you can do more things end-to-end, right? Okay, the fascinating thing is you can do it, right, by violating timing parameters. Oh, okay, that's PyDRAM. More recently, Ismail, who sits over there, has shown that you can do even more in existing DRAM chips. These are not end-to-end prototypes, but these are more characterization of the existing DRAM chips to show that you can actually copy one row, not into just one other row, but also 31 other rows. So you can actually do a bulk copy from one row to 31 other rows with almost perfect success rate. Meaning some bits are not correct, but most of them are correct. This is fascinating, actually. I think this is more than expected because there's a lot of variation that happens in the circuit, right? We're not controlling any of that. We're not designing the circuit to do this operation. We're actually exploiting what is there provided to us. And the person who designed this thing didn't provide it to us thinking that, oh, so you're going to do copying it, right? They didn't design this for copy. They designed it just for access, a single access, right? You can perform the NOT operation with many output operands, and you can perform 16 input AND, NAND, OR, and NOR operations. I'm going to give you examples of this because I think it becomes even more interesting once we go into why this happens. So this is in DRAM row copy. In RowClone, what we used to do is we activate the source row, which brings the data over here, and then we activate the destination row, which brings the data from here to here. Everything is source because you do the copy. In multi-row copy, you activate the source row, which brings the data over here, and then you do a multiple row activation by violating the timing parameters in a specific way. which copies the data from here to all of the other rows. That's the idea. And again, you can talk to Ismail to decide how to do this exactly. But there's a reason why this works, which we already discussed. In the source row over here, this is one subarray. I'm showing you one cell in one subarray, another cell in another subarray in DRAM. Actually, in DRAM architecture looks like this open bit line architecture. Essentially, you have one subarray connected to one end of the sense amplifier, and then another subarray connected to another end of the sense amplifier. You activate the source row, which brings the data into the sense amplifier. And now A is over here, sensed, and then A prime goes over there. And if you actually activate the destination row, this A prime that you sensed gets written into the destination row in the next subarray. So this is how you can capture a NOT operation, except NOT gets captured in the other subarray. How to take advantage of it becomes interesting, maybe, if people are so inclined. Okay. Now, another finding in this work is to show that if you activate 2 rows in quick succession, you can simultaneously activate multiple rows in neighboring subarrays. So these are the neighboring subarrays. I kind of generalized what I showed you earlier. You have a bunch of shared sense amplifiers here, subarray X and subarray Y. And if you actually do a particular activation of row A and then pre-charging and then activation on row B in the other subarray, if you violate the timing parameters heavily, you basically can enable activation of multiple rows over here and multiple rows over here. And the reason is there's some hierarchical row decoder that is here, and which rows you enable depends on the design of the row decoder. Again, Ismail can talk to you about that, and the paper has some more detail over here. Right, Ismail? Yes. Okay, good. And then basically, he's paying attention to something else. So maybe coming up with the next next way of doing in DRAM computation. But why does this work? Let's assume that you can do this, and you can do this in real DRAM chips. If you let's take a look at 2 rows over here and 2 rows over here. These are 2 different subarrays. They're connected through this sense amplifier. Now you do multiple row activation. All of these get activated concurrently. Now what happens to the sense amplifier? Sense amplifier senses the average voltage AB and compares it to the average voltage of X and Y. That's how the sense amplifier operates. This is based on circuit charge sharing principles, right? Each of these cells share their charge, and you get an average voltage. And then each of these cells share their charge, and you get an average voltage here. And sense amplifier compares whether average voltage of A and B is greater than average voltage of X and Y, right? If it's greater, this becomes 1. If it's smaller, this becomes 1. Now you can use this to do bitwise operations. Let's take a look at an example. You basically violate the timing parameter, assuming that you set the values over the reference subarray to VDD, which is easy to do, and VDD over 2, which is harder to do, but people have shown that you could do it, and Ismail can tell you exactly how to do it. Correct? Yes. Can you do it reliably?
Yes. Okay,
there you go. Very reliably. So you can do this. This you can believe, but this is a bit harder to believe, but there's a way to do it actually. Now the average voltage here is set to 3 VDD over 4, right? Now the value you get over here and over here depends on what are X and Y. Now for the value over here to be 1, 3 VDD over 4 should be greater than the average of X and Y. For the value over here to be 0, 3 VDD over 4 should be smaller than average of X and Y. So if X and Y are 1, that's the only case where the value over here will be 0, which means that this is a AND function right at the bottom and a NAND function at the top. So you get the bitwise AND and bitwise NAND. Yes?
How do I ensure if I activate all cells at once that now I have a voltage mosh in each cell, which is not the original value? Do I first copy always?
Yes, you'll need to copy essentially. Yes, if you don't want to lose the data, you will need to copy to the places where you're activating. No question about that. So if you want to really design a system that takes advantage of it, it's going to be somewhat similar to what we did with the MBIT, in my opinion, which I didn't go into the implementation details, but yes, you will need to do that. So RowClone is always important in all of these primitives. Okay, so now you have bitwise AND and bitwise NAND, but you can also imagine bitwise OR and bitwise NOR by setting this to 0 and VDD over 2, right? Okay. Okay, I think it's fascinating. Now the question is, does it work in real DRAM chips? And Ismail showed that in some manufacturers it works. Some manufacturers don't allow you to violate the activate to activate parameter, which is not nice. I think everybody should allow these violations so that we can discover new things. But in some manufacturers, I think this is average across many manufacturers, right? How many? Two in this case. But basically, if this is robustness of multi-row copy, and you can see that you get an almost perfect copy accuracy, right? So clearly, copying is easier. If you want to make it perfect, maybe you need to modify the DRAM a little bit. And it's good to think about how you would do that, because clearly approximate computing doesn't work, right? If I tell you only, well, it doesn't work in many cases. It does work in some cases. Right? It's good to find applications where it does work, and it's good to also make it work for the general case. Okay, so AND, NAND, OR, and NOR is not as easy. Clearly, there's a lot of variation that can happen in the circuit right now because you're activating many rows and you're actually trying to do computation. But still, the success rates are not terrible, right? In fact, in some cases, it's pretty high. And Ismail can explain you why they're so high. But still, 94% is not good enough to do computation. But the purpose of this work is not to show that, oh, you can actually use existing DRAM to do computation. It's to show that existing DRAM has this computation capability, even though it's not designed for it. Now, the key is imagining what else can you do, right? If you actually design the memory substrate to do computation, can I make this more reliable? Can I do some other things if I actually change the substrate? So these are actually fascinating questions, basically. Okay, so basically the answer is we're not smoking pot. I think that's another way of summarizing the thing. But you could give that answer after some number of years. That's the beauty of long-term research, right? I cannot guarantee you that I wasn't smoking pot. But now we're not completely smoking pot. But maybe there's more to do. Okay. Okay, so let's see how much time we have. Any questions? Otherwise, I'm going to give you some other examples relatively quickly. But basically, you can do more things. It's good to ask this question, in my opinion. These are commodity memories that are not designed for this purpose. We're kind of abusing them. But we're showing that they're fundamentally capable of some things: copying, initialization, and or not, NAND, NOR, etc., which is fascinating. But we have also shown that you can do other things using, again, our infrastructure. In this work, we showed that you can actually generate random numbers in DRAM. And the idea over here is whenever you access DRAM, there's some latency parameter, right? If you obey that latency parameter, you get the data reliable. If you, let's say, reduce that latency parameter and access DRAM early before the sense amplifier settles in terms of what it's sensing, you can actually sense some randomness that happens in the bit line and the sense amplifier. And this work is exploiting that. Figure out how long you should access a particular cell in DRAM such that the result that you get is a random value. Sometimes it's a 1, sometimes it's a 0, and you cannot predict what it will be. And use those cells as random number generators. It could be, for example, you could use 100 cells and 100 subarrays, and you could concurrently generate 100-bit, a 100-bit random number. That's the idea over here, which is a fascinating idea. And we showed that in real DRAM chips, you can actually generate these random numbers. Again, this doesn't require changes to the DRAM chip itself. It requires changes to the memory controller to violate the timing parameter. And like many true random number generators, you need to do some post-processing in the memory controller. Okay, and then Atabak also showed that you can do better by activating 4 rows concurrently. And that gives you better, higher throughput random numbers. And more recently, Ismail has shown that 4 is not the magic number. You can actually do 8 rows, and that gives you even higher throughput random numbers. Right? So if you're interested, I think there's a lot of interesting things here. And again, integrating these random numbers to the system is important. And this is Nisa's work that talks about that. We've also shown, again, on real DRAM chips that, so randomness is actually very interesting. Whenever you have randomness, you have the flip side as well, meaning determinism. Meaning some cells are random number generators. Whenever you access them with some latency, you create some random, you basically sense some randomness in the physical circuitry. That's what actually makes it truly random. People have a hard time defining truly random, but usually they resort to, I cannot explain this physical phenomenon, and this physical phenomenon leads to true randomness, which is not always satisfying. But anyway, flip side is some cells, when you violate the timing parameter, always fail. And those cells are different in different DRAM chips, meaning they form a signature of the DRAM chip, which enables an identification mechanism for attestation, for example, remote attestation, which is essentially what a physical unclonable function is. Physical unclonable function is a function that you generate that identifies a particular piece of hardware, right? And this could be useful for many security purposes. You're communicating with the right, let's say, hardware, etc. Nobody swapped this hardware with something else. Right? So we show that this could actually be a very nice physical unclonable function. Again, there are very interesting things in physical unclonable functions that I'm not going to talk about, but this paper discussed it. Okay, if you want to do more in DRAM, you need to modify things a little bit more. This is, I think, a very promising area. And this works, in my opinion, scratches the surface. And the idea over here is to use DRAM as a lookup table so that you can do arbitrary computation. I mean, clearly, you've taken digital design courses. And in digital design, at least when you take my course, for example, I talk about using memory as lookup table, right? And if you use memory as a lookup table, you can implement any function inside memory. It could be a multiplication function, right? You just basically set the truth table of the function, and then using the input parameters, you look up the right location in memory, and that gives you the result of the function. So you could do that over here too with some expense. I think there's more to do in this area, but this can enable like more sophisticated functions in memory. Okay, everything I said, similar things can be done in flash memory. In this work, we have shown in real flash chips, real NAND flash chips, that again, concurrently activating multiple rows provides a bitwise AND or bitwise OR function. And you can make this more reliable. So you can actually get perfect reliability using single level cell mode in flash memory because we modified the memory controller, meaning the flash controller in this case, such that it can separate the distances in terms of voltage across different flash cells. This is fascinating, I think. Existing flash cells are also capable, but in a slightly different way. You cannot do the bitwise majority function, at least the way flash cells are designed today. Again, I don't have time, and we're almost out of time, actually. But if you're interested, there's a lot you can do in flash memory. And more recently, Mayank, one of my students over here, not over here, somewhere over here, maybe online, he has exploited this to actually do homomorphic encryption. So homomorphic encryption is a very bulk bitwise encryption scheme. And it's very expensive, but people are trying to accelerate it so that you can do computation on encrypted data. Ideally, if you have encrypted data, if you have some private data, you don't want to decrypt it, because once you decrypt it, everybody can see it with some methods. If you actually do computation completely on encrypted data, homomorphic encryption enables that. And it's actually very suitable for doing it inside the flash chip using these bitwise operations. And this paper describes how to do that in one way. Okay. I think I've covered a lot. But basically, we've covered processing near memory, processing using memory. And there's a lot more in this. Like if you are interested in emerging technologies, we talk about emerging technologies. Recently, we've extended. Actually, I should extend the author list because Geraldo helped extend this paper to from 50 pages to 99 pages. So there's a lot over here. And there's a lot more to add, actually. We couldn't add everything we wanted to add. It gives you an overview of the state of the art in processing in memory. Actually, we recently wrote a paper which is going to be presented in 2 weeks with Atabak and Ismail that talks about a summary of this. But I will talk about something that's really important, which is really the adoption of this. So you can design any hardware in the end, but it may not be adopted. Like some people may know the story of IBM Cell, right? It's a very interesting hardware. It's a heterogeneous, probably the first heterogeneous processor. It was not adopted because these folks punted on the coherence problem. That was one of the issues. Basically, they said coherence should be handled by the programmer. It was used by Sony PlayStation, but then it was not developed further, right? So adoption issue is really important, essentially. And here, we're not just designing a new hardware, right? New hardware is only part of it. It's really a new paradigm in the end. You're doing computation somewhere else. Even existing theory doesn't explain how to do this in the best way. So we're actually changing a lot in the stack. So there's a lot of barriers to adoption. The good news is people are designing hardware right now. So people are exploring these issues. Once you design the hardware, people can explore software issues also more easily. So what kind of applications benefit? How do you write the software for PIM? How do you ease the programming so that most people can easily transfer to this? So a lot of Geraldo's thesis actually answered some of these programming and systems questions. How do you interface with it? What kind of compiler and hardware support do you provide to ease programming? How do you do coherence, which is hairy? How do you do synchronization? How do you do virtual memory? You covered virtual memory last week. You may actually have questions. Okay, I'm executing something in DRAM. Who handles virtual memory, right? That's a very valid question. And probably you've seen that virtual memory is a mess. And I think virtual memory is probably the hairiest issue that we have in our systems today. It needs to be re-examined completely, in my opinion. Okay, other stuff like isolation, if you're executing multiple applications, if you're executing a single application and you're doing processing in memory and also CPU or whatever compute unit you have is accessing memory, how do you handle the conflicts, isolation, scheduling, etc.? How do you design the runtime and compilation systems? How do you actually do the scheduling of code to processing in memory or processing using memory? How do you do the data mapping? Data mapping that you need for a processing in memory engine is different from the data mapping that you need in a processor-centric system. And these actually conflict with each other. And how do you actually maximize locality so that you can do better processing? How do you do the access and sharing control? So there are a lot of actually interesting issues. And then how do you design infrastructures? So I think all of these need to be researched. They're being researched, actually. There's more research that needs to happen in all of these, in addition to the hardware, etc. But probably the hardest one is the mindset. Meaning all of these are problems. You can see these as problems, but you can also see these as opportunities, right? So if you actually look at this and say, oh, I want to change all of these at once, it's not going to be easy. But over time, these can be changed. If you change our mindset, you need to change your mindset. You cannot say, oh, I'm going to use the existing data mapping mechanisms and I'm going to make processing in memory work. It's not going to be easy. It's good to, again, take the 10-year-old approach. What is the right thing to do to enable this? That's the researcher's mindset. And that's also a kid's mindset. And they will be honest with you again. So it's good to be honest because you're not going to be able to do everything without changing things. Right? Okay. Okay, this is Geraldo's thesis. If you're interested, he graduated, I think, well, 29th of April. And you can look at his slides. His thesis is not available yet, but we'll make it available at some point. And I think there's more to be done in this area. This is just scratching the surface also. Geraldo developed some programming models also for memory. But let me give you some, again, we don't have a lot of time, but I'll kind of rush through some papers that talk about this. If you're interested, you can go. This is a work that we did with NVIDIA. Our goal was to actually offload computation from a compute-centric GPU to these memory-centric GPUs inside there in the logic layer so that we can actually reduce the data movement overhead in a GPU system. And we did this completely transparently to the programmer. It's called transparent offloading and mapping. So there's some things to be gained if you do it completely transparently to the programmer, but it's not, if the programmer goes and modifies things, you can do better, I think. This is Geraldo's work that I will not talk about, but you can look. This is a framework that we developed for processing in memory. That's a high-level framework that expresses operations in a high-level, let's say, primitives, and that can get compiled. Compiler can optimize things. So basically, I think these high-level frameworks are very important because you don't want programmers to inject instructions, right? Either the compiler does that, or programmer programs in a way that is easily compilable such that you can take advantage of processing in memory. And this is not the best work. Actually, Geraldo showed that this is better than simple PIM, but that's how research evolves. There's more work on identifying like which workload should benefit and what you should offload. Again, I will not talk about this. This is Nika's work. You can talk to Nika over there with the hoodie. So, okay. So this takes into account some things that, for example, Tom, the paper doesn't take into account, instruction offloading and the data movement overheads. And then how to keep it simple is important. These are some works. Again, I will not go into the details of all of these, but enabling instructions to be offloaded is important. Coherence, now we're getting into hairy issues. These are some works that we did where we showed that existing coherence mechanisms are not enough if you partition work between processor and memory. So you need to come up with new coherence mechanisms. Synchronization, and again, virtual memory. This is the hairiest issue. I don't think we have a solution to virtual memory yet. So it's a good problem, but maybe we need to rethink virtual memory for processor-centric systems as well, because it's not measuring up, in my opinion. So we develop a lot of infrastructure. These are actually sampling of our works. There are other works also, clearly, that will not fit in one lecture. But evaluation infrastructure is also important. So, okay, hopefully I've convinced you that you need to revisit the entire stack. I'm almost out of time. I guess I'm approximate computing. I'm almost out of time. I can use approximate computing to this advantage, as you can see. But let me finish. Essentially, we want fundamentally efficient and high-performance architecture. If you want both and also sustainability, you need to be data-centric. And also, I also think actually robustness, security, a lot of metrics can be improved by being more data-centric. But that remains to be proven. So we want to design architectures with minimal data movement. I've covered in this, let's say, dense lecture how to enable computation capability in memory, focusing on DRAM especially, and major recent advances. I've given you some examples that show orders of magnitude energy and performance improvements. These actually exist even in existing systems like UpMap. So there are actually applications that benefit a lot from the limited capabilities of real processing in memory systems today. I did not talk about those. And fascinatingly, unmodified DRAM chips are already capable of computation. So I think going forward, we should really be 10-year-olds and answer the questions, how do I design things that can compute everywhere, let's say? Design memory as a combined computation and storage substrate, other than inactive, dumb storage substrate. So for this, clearly, a lot of things need to change. Design mindset and flow should change also. Most importantly, the mindset should change. I think the future is bright, basically, but there's a lot of research and design that needs to be done. I like this example because even though I don't know much about this, the people who know a lot about this say that there is no dichotomy between processing, storage, and communication in this thing. Okay, so we have a lot of tutorials. If you're interested, you can learn more. We have some upcoming tutorials. If you decide to do work, you can present. And there are a lot of open source tools. Okay, I'm going to skip this, but there's a lot of industry. Maybe this is good to look at. There's a lot of industry interest in this, even though industry is in an interesting place, right? They don't want to change a lot. That's how they want to make money, right? If you don't change a lot, if you invest in the processor-centric infrastructure, that's good. But they also want to innovate. So industry has a lot of interest in actually enabling this sort of processing in memory today, much more so than they used to be like 10 years ago. So there's a lot of, I think, positive movement in this direction. There are even discussions in JEDEC, for example, which is the slowest moving body in the world, perhaps. Maybe they will disagree with that. But essentially, they discuss how to interface with processing in memory devices, for example, today. OK, I think a lot of people did this work. You can see some people here. I'm already out of time. And you can actually see some people over here. A lot of people around you are doing processing in memory work, and you can talk to them. Hopefully, this was interesting. I will not keep you longer, but if you have questions, feel free to ask right now or later. OK, I'll see you next week then.